Thank you for inviting me to give this seminar in these strange days in which we are rediscovering that COVID is within us. So that's a good opportunity to discuss about science in these strange days. Okay, yes, I'll say I slightly changed the title, but this is not an error. It's exactly the same title. The reason being that when we talk about fast material, I'll say the head of this new family is germinotelluride, so that there is no big difference. Okay, so let's start now with my talk. I'll say just some credits to people contributing to this talk, which has been, I'll say, quite a long travel along this story of fast materials. So first of all, Christian Rinaldi, he was a postdoc, now he's, I'll say, assistant professor in our group, and our collaborators in Milano, people from electrosynchronization facility in Trieste, where we have been carrying out the spin polarized photoemission experiments. University of North Texas for calculation on spin transport, group of Nardelli. Silvia Picotti, of course, has been, I'll say, the theoretician discovering this class of materials. I remember the day when Silvia called me for asking me, what can we do with these materials? And in these years, we have been working experimentally on this side. And then people from PDI producing films, and people from Thales and COA for the experiments on spin charge conversion on this material. Okay, let's start from the outlook. I will start to introduce now the class of material which is named FESC, ferroelectric Rashba semiconductors. And then I will try to see what are now the experimental proof that they can really work, starting from the proof of concept of the dependence on ferroelectric states of the spin texture with a strong relation between the spin and ferroelectric states of this material. And then the possibility to control the ferroelectric state using a gate in a device, which is not just something that you can do with the PFM, with an AFMT, but this is something that can be applied to a device, a real device. And then, which is the core of this talk, the demonstration that we can really control the spin-to-charge conversion at room temperature at ferromagnet germinotelluride interfaces. So let's start with the introduction of ferroelectric Rashba semiconductors. These are a class of materials introduced by Silvia Picotti in these theoretical papers, in which you have the coexistence of three features, which is, I'll say, ferroelectricity first, but also the fact that you're dealing with a semiconductor, which is somehow unusual because in general ferroelectric materials are oxides, insulating materials, and the presence of Rashba effects. So you have these three corners here, ferroelectricity, semiconductivity, Rashba effect, and everything is combined the same material with the possibility of achieving new functionalities. Now, the interesting story is that the entity of the effect, especially in terms of the Rashba effect, which is a special splitting of the bands, is not negligible at all. It's really large, with an energy splitting of 220 millielectron volt, which means you can work at room temperature. And this is really the key advantage of this class of material. So let's start from, say, Rashba, and everybody knows what's the case of electron parabola in this case. And now what happens if you have a two-dimensional electron gas in which you switch on an electric field? You typically have this splitting of the bands. And in these bands, the key parameter is this energy separation, which is ER. As I told you, in germinotelluride, it will be on the order of 230 milli electron volts, sorry. So the interesting point is that here you have the so-called spin momentum locking, which means that the spin will be always perpendicular to the wave vector of the electrons. And this is seen here in this three-dimensional sketch of the bands, in which you see that there is an outer band in which the spin circulates clockwise and an inner band in which they circulate counterclockwise. But okay, in general, you cannot change it in two-dimensional electron gas if you don't change, I'll say, the direction of the electric field, which is something which is volatile. And the fast material, the beauty of the story is that The way you break the inversion symmetry and you give rise to Rashba effect is the fact that you have a polarization, which is a non-volatile entity, so that you can now play with the polarization. When the polarization is upwards, the sense of circulation here is clockwise in the outer bands. If the polarization becomes now inwards or pointing downwards, you see that you reverse the sense of circulation. So, and the idea was, okay, we can play with these materials in order to realize devices in which you have a gate, you control the ferroelectric polarization, but this means that you are controlling also the spin. It's a way for controlling the spin texture with the ferroelectric polarization. What about germanium telluride? Germanium telluride has this structure here, and due to some lattice distortion, you develop a polarization along the 1-1-1 direction, this pseudo-cubic description. Looking now at the energy dispersion of bands, you don't find exactly what you find in a 3-electron model for, I'll say, 2-dimensional electron gas, but you see that the shape here is very similar to that of Rashba bands, ideal Rashba bands. And the beauty of the story is that the energy separation of these bands here is high, 250 milliton or something around 250. Now, the shape of the iso energy cuts, okay, is not simple like in case of the electron parabola, but you see you have some stars here, and the result of a calculation by Silvia was, okay, for upolarization, sorry, you have a sense of circulation of the spin which is different from that you can have for the down polarization. This was, I'll say, the beginning of the story, and now let's try to see what happens in practice. So we found people from PDI, a group of Raffaella Calarco, who were really very good in producing nice films by MBE on silicon 111 substrates. And okay, it's not so easy to grow germanium telluride, but the quality was enough to study the peculiarity of bands, also with reference to, I'll say, angular result photoemission experiments. And this is one of our first images of the bands obtained in collaboration with a group in Berlin. And it was a measurement carried out at Bessie. You see the typical shape of Rashba bands, even though the Fermi level is here. And the reason being that germanium telluride is a p-type material due to germanium vacancies, so that the Fermi level is cutting the valence band top. Okay, the bands are okay, but the problem was, how can you play now with the ferroelectric state? It's not so easy to carry out an experiment in which you pull your ferroelectric film, because in principle with the spin and angular result photoemission, you need a surface, a clean surface. Having an electrode, the top electrode, it's a problem. So we developed this method, which is a surface engineering method in which we obtain different polarization just by creating different termination of the film. And the idea is this one: you can have a germanium terminated or a tellurium terminated germanium telluride films. And in the two cases, due to the different termination, you will have a polarization pointing upwards for tellurium termination and downwards for germanium termination. And the way you achieve this different, I'll say, termination is something which concerns the sample preparation. We have a tellurium capped film. So with different decapping temperature, we can achieve different termination. And by PFM, we check that the pristine state, say the average state of the ferroelectric polarization, which is the result of this treatment for the sample preparation, is different in the two cases. So in case of tellurium terminated, it's outwards. In case of germanium terminated, it's inwards. This is a sketch of, I'll say, it's a summary of PFM measurements carried out. And when in this color code, when you have this dark brown, this means that the polarization is outwards. With this other color, with white brown, you have the polarization pointing inwards. And you see that, especially here, it's clear that the pristine states correspond to a polarization inwards, but we can be able to write now something which is the opposite state of polarization corresponding to this picture frame. So the idea was, okay, we are able to prepare a sample in a pristine state which has a polarization pointing, as in this case, downwards, or as in this case, outwards. And we can also write domains, which means that it's really ferroelectric, which can be written. And in these experiments, which is a spin polarized angular result photoemission experiments, we really checked that we reverse now the sense of circulation of the spin when we change the polarization. And this is done looking at the bands here without entering the details. It's just, I'll say, a sort of prerequisite for the talk today. But what is shown here is that looking now at the energy band dispersion here, you see here that you have two different bands. One is blue, the other is red, and they should be associated to a different spin. This is exactly what you find in practice, because when you look now at the spectra for the two spin channels, you discover that, okay, these 2 points corresponding to these two peaks have different spin direction. This is exactly what you expect for a spin momentum locking. The spin is perpendicular to the momentum, and the two bands here, the two Rashba bands, you have opposite spin. As you can see here, this is the estimated polarization. So looking now at the spin texture, this means that for a tellurium terminated surface with the polarization upwards, so you see that the sense of circulation of the spin is clockwise in the outer bands and counterclockwise in the inner one. But when you move to the germanium terminated one with the polarization pointing downwards, it's the other way around. You see that in the outer bands, the circulation is counterclockwise, and in the inner one is clockwise. So it's exactly the opposite of what was found here. And this was the demonstration that, okay, it works. I'll say the original calculation by Silvia are real observed in practice, which means that you reverse the ferroelectric polarization, you reverse the spin texture. So the idea here is you can control now what? The spin texture by playing with the ferroelectric polarization. But at this point, we were facing a problem, which was, okay, we can prepare different surfaces in a pristine state. How can we write now a different state in a real device? With a PFM, you can write domains. This was demonstrated, but this is not a real device. So to do that and to be able to control the ferroelectric states, we developed now a way for a controllable microscopic ferroelectric switching. And the idea is this, something related to the theory of ferroelectric diodes, dating, say, 1994, something like that, the theory. You see this paper here by Blom and co-workers. So just looking at the IV characteristic of, I'll say, of the gate. You see here the structure. We have a metallic gate on top of germanium telluride film with, I'll say, an interlayer, or without it. It doesn't make a big difference. And you can try now to look at the IV curve. It turns out then, when you pull your structure by applying a positive voltage, in this case plus 10 or minus 10 volts, you obtain a different IV curve. And typically you have a higher conductance in case of a positive pulse, pulse applied here, okay, at the top electrode. What's the reason of that? The reason is that you are changing now the barrier profile of the Schottky barrier, that you have the interface between your semiconductor and your metal. And you have now a situation in which, for a positive, I'll say, applied pulse, you have the polarization which is pointing parallel to the built-in electric field, and you have a narrow, okay, a narrow depletion width, which means a high conductance, as in this case. While for the polarization which is pointing in the opposite direction, we have a wider depletion width, which means a low conductance, okay? But the beauty of the story is that you can now follow the ferroelectric states just by looking at the conductance of your gating electrode. And this is shown here. This is an hysteresis loop of the conductance after application of pulses from minus 10 to about plus 10 volts. And you see that you have an hysteresis which is somehow connected to the ferroelectric state. Now, just to give you some information about the reliability of this story, it's really reliable because it's something which persists up to 10 to 5 cycles that you can apply. Here is just the percentage variation between the two states up to 2000 cycles. You see that there is no appreciable change here in the percentage variation, which means you have two distinct states. And also the writing time is not so high because it's below 250 nanoseconds, which has been the minimum duration of pulses that we have been using during last measurement. Probably we can go down. But this is something connected to the electrical behavior, which is also interesting because in principle, you can also use it as a sort of memoristic device. But for the present talk, the interesting story is that if you can really now control the ferroelectric state just by looking at the, I'll say, the impedance and the IV curve of your gate electrode, this means that you can really control, have a good control of ferroelectric state in a device, and also follow what is happening when you're trying to perform some spin to charge measurement, spin to charge conversion measurement. And okay, just to say that we have something which is similar to ferroelectric memristor, obviously. And let's now move to this experiment, which is very relevant to me because it really demonstrates the connection between the ferroelectricity and what we are seeing in terms of the conductance change. This is a clever experiment carried out by Christian, in which he realized a device, is this one with the silicon nitride germanium telluride, I'll say, bilayer. And then on top of that, you have your metallic gate electrode with, I'll say, a very thin layer here, which allows for a PFM measurement, okay, through the metallic gates, and another region in which you can apply now a writing pulse. And by measuring now by PFM, I'll say, the ferroelectric map in this region, he was able to see what happens when you apply different pulses, starting from +8 volt. Here you see the map of the piezo force microscopy phase. So there is a big region in blue corresponding to polarization pointing downwards. And when you move to negative or right pulses, you see that this blue region decreases in amplitude till you reach a red region corresponding also to polarization pointing upwards for -8 volt. And at the same time, it was possible to measure the change in the impedance. And this is the result. When you look at the PFM phase, you have with continuous line, this hysteresis loop, which is superposed to the resistance loop, which means that really the resistance change is following the ferroelectric states. And you can also model the resistance change using a parallel resistor, a very simple model. Okay, that's a very important demonstration that we are really looking by an IV measurement to the ferroelectric states. I will skip this aspect here. So we are ready now for the demonstration of the room temperature reconfigurable spin to charge conversion at the ferromagnet germanium telluride interface. Okay, what does it mean? It means that, okay, people would like to achieve a system in which you can play with the spin just by playing with an electric field. And in this very, I'll say, very well-known paper by the French group in Paris, they found that if you realize a layer structure in which you have a ferroelectric layer, in this case it was strontium titanate at very low temperature after application of the I field, in connection to a two-dimensional electron gas, which is from the interface with the metallic layer, you can really, I'll say, observe a Rashba effect, which determines a change in the spin to charge conversion when you change the polarization in the ferroelectric layer. So it's a layered system in which you exploit the two-dimensional electron gas in proximity to a ferroelectric material. And what they found is that even though at very low temperature, you can really change the spin to charge conversion when you inject now a spin current and you observe now a charge current. You can change the spin to charge conversion by changing the ferroelectric state, as it is shown here. Okay, that's a very beautiful paper, a very, very nice, I'll say, demonstration of the concept. Obviously, there are some limitations. The operating temperature is 2 Kelvin. It's not real ferroelectric material. It's a field-induced ferroelectric order. And obviously, it's not CMOS compatible. What I'm showing you today is that in germanium telluride, in principle, you are CMOS compatible. You are not dealing with a ferroelectric induced order, but is really a ferroelectric material. And the operating temperature for this spin-to-charge conversion is 300 Kelvin, which means room temperature. So the first experiments we carried out a few years ago was this experimental spin-to-charge conversion by spin pumping experiments in collaboration with Fert and Laurent Villa. At that time, we produced this iron germanium telluride heterostructure, which is fully epitaxial, and we measure by spin pumping that there is really a spin-to-charge conversion. The idea of this experiment here is quite simple. You have your ferromagnetic layer, you apply this DC field HDC pointing in this direction, the green arrow here, and then you apply a radio frequency field in this direction. Then you excite now a precession, and when you are at the ferromagnetic resonance, there is a channel for momentum relaxation which corresponds to this injection of the spin current here, JS, in germanium telluride film. And what happens is that if there is any spin to charge conversion, there will be now what? A current JC flow in this direction that gives rise to a voltage drop which can be measured. So by measuring this voltage drop, you really observe, and we observed and we published that in a few years ago, that there is a peak now in the spin to charge conversion, the charge current JC, in correspondence to the ferromagnetic resonance. But at that time was really impossible to control the ferroelectric states. Now, on the basis of what I have shown you before, now we are in condition to follow what is going, when we apply now a writing path. And this was the results that we have now tried to publish. And the result is this one. Okay, now we have our iron germanium telluride structure. This is now the schema of the experiments. Sarah Barot, a student of our group, went to CEA in Grenoble. They cut some slices, and they were able to put them now in the cavity in order to apply now some fields, some electric field in order to pull now the germanium telluride layer, and also to measure by spin pumping the spin to charge conversion efficiency. As I told you before, now the beauty of the story is that by applying different writing voltages, pulses, we are able to follow what is happening. And here you see the typical conductance hysteresis loop, which corresponds to the fact that here you are in a ferroelectric state, and you can switch to the opposite ferroelectric state. So you know in which state you are when you measure. And this is the typical measurements. Okay, in this case, in this column, you have the case of a slice cut along the ZA direction, which is a peculiar crystallographic direction of germanium telluride. This is a ferromagnetic resonance for different applied voltages. And you see here the interesting story, which means, well, for the polarization pointing downwards, you have this blue curve with a positive charge production, and for the polarization pointing upwards, the red curve, you have a negative charge production, which means that you can control now you can tune the sign of the charge, spin to charge conversion by playing with the ferroelectric state. So the interesting story is that we are changing something just by changing a variable of state, which is stored in ferroelectric state memory. And along a different crystallographic direction, you have a similar curve, but interestingly enough, it changes sign. That's interesting demonstration that is something really connected to the crystallographic structure of our material. And probably the most relevant result is this one. It's, I'll say, the entity of the charge production is a function of temperature. And you see that from 100 Kelvin to 300 Kelvin room temperature, it doesn't change. So that's a very interesting result, because we are no more working at 2 Kelvin. We are really working at room temperature. Now, what about the size of the effect? Because it's really something that could be used for some interesting application. The question is, what is germanium telluride in comparison with platinum? And this is the experiments carried out in the same experimental apparatus on two different slices. One was platinum and cobalt iron boron, the other one was iron and germanium telluride. And you see the two ferromagnetic resonance in blue, germanium telluride, in red, the case of platinum, and also the charge production curves here. As you can see, I'll say the entity, the order of magnitude of the effect is the same. It's 66 milliamps, millitesla to the minus 2 meter to the minus 1 for germanium telluride and 77 for platinum, which means that the entity is very, very similar. So that's a good news, because it means that in principle we can now work on germanium telluride like in case of platinum, for instance, for producing spin orbit torque and some materials, having in mind that in germanium telluride we can also have this additional degree of freedom, which is the possibility of store a degree of freedom, which is also the variable state written in the ferroelectric state. And what about the physical origin? So without entering the details of the calculation, because I'm running out of time, I'll say Marco Nardelli performed some calculation just to see if bulk spin-Hall can explain what we are seeing, and the answer is not, simply because, okay, when you revert the polarization, nothing changes. When you calculate now the spin-Hall conductivity, they are unchanged, totally unchanged. As you can see here, for P out and P in, you have the same elements of the tensor. But if you introduce now some asymmetry, which is that typically found in our iron germanium telluride silicon structure, it was done not exactly for this structure, but for a slab with two different P out and P in, I'll say, configuration here, and a different termination. They found that you can really discover that for P in and P out, the sign of this element of the spin-Hall conductivity tensor, which is that really connected to our experiment, it changes sign here in agreement with our experiment. So the final message is that, okay, inverse spin-Hall could be enough for explaining what you are seeing, even though we cannot exclude, let's say, other effects like inverse Edelstein Rashba effect, as it is also depicted here. In case I can explain the story, but in this case, you suppose that you are injecting a spin current which creates some spin accumulation, displays the Fermi surface, and this gives rise to a current. I'll say the message is probably spin-Hall effect could be enough, also because in terms of number, it could really explain the strong similarity between what we see for platinum and for germanium telluride. And that's all. Say, I have been very glad to give this seminar to show, I'll say, the advance of our research, which means that nowadays we're in condition to say that we have the possibility to control the ferroelectric states of the germanium telluride and also spin to charge conversion effects at ferromagnet germanium telluride interface. And what's the perspective of this work? Obviously, try to use the possibility also to pattern spin texture by, for instance, writing different ferroelectric texture in our materials to perform perform experiments on more advanced devices, playing with, I'll say, spin texture patterning in our devices. So that's all for your attention, and I'm ready for questions if there is any.